So I found this Lexus commercial pretty interesting, in part because I wasn't entirely sure what they were advertising. So what they said was, here I've got a picture, right, of a car which is 4,000 feet in the air, and they're going to drop that car from rest, right? And that car is going to fall at g, at acceleration due to gravity, 9.8 meters per second squared. Now, because we're talking about two dimensions here, two separate dimensions, I'm going to call that the y, the delta y, and because delta y is in the downward direction, 4,000 feet, and 9.8, and the acceleration due to gravity is in the downward direction, let's just call down the plus y direction. Okay, great. Then it's got a car which is going horizontally. Let's call that the x direction. But I'm unclear what they're saying. Are they saying that this car can accelerate faster than the acceleration due to gravity? If this car can accelerate faster than the acceleration due to gravity, then indeed it can beat the car falling because they're going the same distance, the same initial velocity, etc. So let's first ask the question. I don't even know what it's asking. So is it saying that the car can accelerate faster than gravity? So what I took that to mean is we're saying that if the acceleration of the car on the ground, A, is bigger than the acceleration of the car in the air, G, and both start from rest, the car on the ground beats the car from the air. Okay, so maybe they're just saying it's got great acceleration, right? 0 to 60 in 2.5 seconds, whatever. So let's go ahead, and so I haven't really asked a question, but the question I really have is this reasonable? So first of all, the question is what are they trying to advertise? I actually don't really quite get it. But the second question is this reasonable? So to make this assumption that what they're saying is A, almost seems to be what they're saying. So let's just see if that's reasonable. So to answer the question, is that reasonable? What do we want to determine, right? That the car falling is going to be falling at a constant rate, constant acceleration, 9.8 meters per second squared, and it's going to have some final velocity. The car on the ground has to have a bigger final velocity, right? If it's accelerating higher, it's got to have a bigger final velocity. It's the only way it's going to beat the car on the car falling. At some point, it's got to have a higher velocity than the car falling, than the fastest the car falling. So anyway, so the question is if you accelerate at 9, so the question I really want to ask is if you accelerate at 9.8 meters per second squared for 4,000 feet, what is your final velocity? That, I think, is going to answer the question. Oh, okay, so that's reasonably what they're trying to claim. I'll just put the subscript, right, just to make sure we know. We want to know what's the final velocity, or what's the final speed, right? In the case of the falling car, its velocity is downward. In the case of the car on the ground, its velocity is to the right. So this is easy enough to do. We just have to do a unit conversion. Hey Siri, how many feet are in a mile?
It's 5,280 feet.
Okay, we all knew that, right? So therefore 4,000. Wait, why did I want to do miles? Whoops! I wanted to just convert that to meters. Darn it! How do I know I want to convert it to meters? Well, because G is in meters per second squared, is MKS units. So we need to convert this to MKS units. So Siri, how many feet are in a meter?
3.28 feet.
Okay, so 3.28 feet in 1 meter. So we're talking about the car going 1,220 meters. All right, so let's just see then. All right, so let's go ahead and we know that delta x is 1,220. We know that, well, I just wrote that, that it's got an initial velocity of 0. Final velocity is what we're looking for. Acceleration is 9.8 meters per second squared, or has to be just higher than that, but let's just say it's 9.8 meters per second squared to answer the question. I think that picture has everything. We could have drawn it for the car on the ground or the car in the air. It doesn't matter which one. We can do either one to figure out what the final velocity is. If they meet at the same time, let's say what's the final velocity? And we can go ahead and write down our three kinematic equations, write what we know and what we don't know. I'm going to skip ahead and say, oh, okay, we can just use v equals v0 plus at. Therefore, v is equal to 0 plus positive 9.8. So I skipped a lot of steps here, times t. Whoops, that equation is not going to work for me. Let me go back to my process. Okay, I'm going to write delta x is 1,220 meters. It's positive. If we do the horizontal trip, a is positive 9.8 meters per second squared. V final is what we're looking for. V initial is 0. T is unknown, and we don't care about it. So what I do want to know, we want to solve for that. We've got our 5 unknowns. Our equation, 1/2 at squared plus v0t, v equals v0 plus at, v squared equals v0 squared plus 2a delta x. Okay. Now what we want to do is figure out what equation to use for v. Well, since we don't know time, let's go ahead and use the third equation, plug into that one, and we get v squared equals v0 squared plus 2 times acceleration times delta x, which is 1,220 meters. And so therefore, v squared is equal to 23,912 meters squared per second squared. So then plug that into your calculator, you get plus or minus 154.6 meters per second, right? When you take a square root, you get plus or minus. But in this case, everything's moving in the positive x direction if we're talking about the car that's moving horizontally, or in the positive y direction if we're talking about the car that's falling vertically. So all we have to do is keep the positive quantity, and the meters per second are the correct units, just to check. And so the answer is 154.6 meters per second. So is that a reasonable velocity, right? So that was the question. Is that a reasonable velocity? And you might say, well, for a car, but you're forgetting that this is meters per second, not miles an hour. This is meters per second. There is no possible way that a car could be going that fast. That's about 300 miles per hour. Do the conversion for yourself, but remember, it's about a 2-to-1. 300 miles per hour. There's no way that car is going that fast. So that must not be the question they're asking. They must not be asking if the car on the ground, or claiming that the car on the ground can accelerate faster than the acceleration due to gravity. So what are they claiming? To remember, what they're claiming is that the dude in the air is going to reach the ground before the dude on the ground is going to reach, is going to pass under the dude in the air before the dude in the air reaches the ground, right? So we're comparing this one to that one, the car, the dude, right? We're calling the car the dude. But the car on the ground is going to reach the point. It's going to reach the point where the car falls before the car that falls. But if you look back at the commercial, you see that it actually already has an initial velocity. So it does have an initial velocity. So they're not claiming that the two accelerate at the same rate. Perhaps what they're claiming is that the car can go fast enough that if they're the same distance away, it can beat it. It's a little, I'm not entirely sure what kind of claim that is. But in any case, I think what they're claiming is, what is the speed needed? The initial velocity, if it's traveling at constant velocity, if the horizontal car is traveling at constant velocity, to beat the falling car. Assuming that's what they're asking. So we go back and we set up this problem slightly differently, and we just say, okay, in the new problem, we're going to say v0 equals v, right? There's some constant speed, and the question is what speed is that constant speed in order to beat the falling car? And so let's go ahead to 2 pages ahead, and let's say, okay, so for the car going to the right at speed v, it's going to cover 1,220 meters, and we know that its initial velocity is plus v, and its acceleration is 0, right? We're saying it's not accelerating. Its delta x is plus 1,220 meters. I still define this direction as plus x. T is unknown, and v final is the same v. It's traveling at constant velocity. And for the car that's falling, we're saying that v0 equals 0, A equals, and we'll call down the plus y direction, plus 9.8 meters per second squared. V final is whatever that is when it hits the ground. Time, unknown, and delta y is equal to plus 1,220 meters. Okay, so that's setting up the problem where all we've changed now is that the horizontal car is traveling at constant velocity. So now how do we answer the question, right? The question is basically, right, you got to think about how do we answer the question, what speed is needed? Well, how do we know what speed is needed? Well, the times must be the same. In other words, when the first car, let me do a different color, when the horizontal car goes 1,220 meters, it better do it in a smaller amount of time than when the vertical car goes 1,220 meters. So we can compare the two times, and all we need is for this one to be just higher than that one, and then it beats it. So basically, we set the times equal to each other, and then we can say it's just got to go a little faster than that. Okay, so we can write the equations of motion for the x direction. Delta x equals 1/2 at squared plus v0t. Oh, but the acceleration is 0. So delta x equals v0t. And I'll tell you, the next two equations don't matter. Let's write them down for the y direction. Delta y is 1/2 at squared plus v0t. And again, just be careful here that the acceleration for the horizontal car is different than the acceleration for the vertical car, right? These things, I should be putting subscripts on these, like a sub x and a sub y. But I haven't been careful because I've just been separating the two motions. Okay, so, and then v squared equals v0 squared plus 2a delta y, and v squared equals, and v equals v0 plus at, a sub yt. Okay, I just put the subscripts again in order to separate, like make sure we're talking about separate variables for the car traveling in the x direction and the car traveling in the y direction. And sorry about the scribble there, but okay. What I had said about the car in the y direction, the car in the x direction, the horizontal car, is that the second two kinematic equations don't matter because let's just do a real quick aside here. If these two equations, if the acceleration is equal to 0, what do the two equations say? Right, the first equation says v squared equals v0 squared. The second equation says v equals v0. What they both say is that the velocity is constant, right? If acceleration is 0, velocity is constant, and we already know that, right? The velocity is constant. That was the point of for this dude over here, right? The velocity is constant, and we know that, so we don't need the second two equations. Okay, so we can go ahead and say, okay, well, for the dude on the horizontal dude, delta x equals v0t, delta x plus 1,220 meters equals v0 unknown, t unknown, right? v0 is what we want to know. T is going to be the variable that allows us to connect to the vertical dude. So the vertical dude, we can go ahead and say 1,220 meters in the y direction is equal to 1/2 times plus 9.8 meters per second squared times t squared plus 0. And we can solve for t. T equals 1,220 meters and we can just divide that by 4.9 meters per second squared. Take the square root in order to solve for t. And we find t equals 15, sorry, not 4, equals 15.8 seconds. You just say, oh, the other car has to do it in less than 15.8 seconds. So if we go ahead and just plug in 15.8 seconds here, that'll be, we know that the velocity just has to be higher than that. So this is the kind of manipulation you need to be doing with these problems, is you need to see those kinds of connections. Oh, one car is going takes 15.8 seconds. The other car has to take quicker than 15.8 seconds. So if we go ahead and put in 15.8 seconds, we can just say it's got to go quicker than that. So we got v0 equals 1,220 meters divided by 15.8 seconds, which gives us 77.2 meters per second. So this is actually 173 miles per hour, And so then the question is can a Lexus drive 173 miles per hour over 1200 over a mile distance? And the answer, I believe, for those of you who know about cars, is yes. That is a reasonable, although albeit very fast, speed.